Hi everybody, today's lecture is going to be talking about acids and bases, which are a special kind of solution made of water and certain materials which give away extra protons, which causes them to have extra chemistry that's a little bit different than other types of solutions we've been talking about, which is why they have their own special classification as either an acid or a base. The things, so to kind of start off with that, what we'll first do is just describe what these are. So what is an acid and what is a base? In acids and bases, there's two commonly used definitions to describe those. And one of them they're based on different groups that kind of saw these. So the original way of describing acids was what's called an Arrhenius acid. And that's any substance, so any solution that when you dissolve it in water, so any solute that when dissolved in the solvent water produces what are called protons or hydrogen ions. So that's just a hydrogen atom without any electrons. Hydrogen normally has one electron. We're going to take away that electron, make it have no electrons, which means it still has one proton and then therefore a positive charge. So an example would be something like HNO3. HNO3, if you dissolve it in solution, actually turns into H plus and then NO3. So you can still see everything's there. There's still one hydrogen, one nitrogen, and three oxygens. But the hydrogen's gone away from that NO3 molecule and it's hanging out in solution by itself. And then the NO3 is by itself as a negative ion. The same way that like Na and Cl will split up to make Na plus and a Cl minus, HNO3 will split up to make an H plus and an NO3 minus. The only problem with this description is that it turns out actually that there are no H pluses alone in solution. So if you were to look in water after adding HNO3 or any acid, you wouldn't see any H plus on its own. What instead you would see is H3O. So that's where the second definition of the Bronsted-Lowry, which is a little bit more accurate description, but again, it's the same thing. These are losing one of their protons. So HNO3 gives away its proton, the proton goes away, and it actually gives that proton to another substance, the water, and it turns water from H2O into H3O. So it's the same net effect. There's still an H that's positive, it's just an H that's positive attached to a water molecule rather than on its own. But you still get that NO3 molecule in the end. So these are acids. So acids are basically things that make the H3O concentration of a solution increase. So if there's a lot of H3O, that's positive water with three protons on it. And that can be doing some damage depending on what kind of chemistry or what kind of systems you have. So this would be an acid system where the HNO3 is the solute, and when it's dissolved in the solvent water, it creates an acidic solution with H3O and NO3 minus. And bases are similar. Bases are things that produce OHs, or kind of by the second definition, something that accepts a proton. So if there is an H3O or an H, that's the thing that's going to take the proton. So the H2O could accept a proton to become H3O. OH could accept a proton to become H2O. These are just molecules that, this is where that proton goes. So right, if the proton goes into solution from an acid, it has to go somewhere, and it goes to the base. So it goes to the base as either H3O, or it goes to the base, the OH, and becomes H2O. So acids and bases are basically solutions that contain H's or OH's, or H3O's and OH's, and they have certain chemistry properties from that. So they'll interact with each other. If you have an acid, generally somewhere else there's a base. So acids and bases usually react. So if something is an acid and it's donating a proton, well, it has to put that proton somewhere, and that proton is going to go from the acid, which is going to donate the proton, and that's going to go to the base. So if you do that, you're going to have one thing that loses a proton and one thing that gains a proton. So for example, our HNO3, right? The HNO3 is going to give away this proton. So this is the acid over here, and it's going to give that proton to the water. So the water is going to be our base. So here the water is accepting the proton, and it goes from H2O to H3O. So the water is the base because it gained a proton, and then the acid, the HNO3, is an acid because it lost its proton. The H went away, and it went on to the H2O here. So you can see the proton being transferred, and then it went to the other molecule, so the NO3. But when you look at that, you'll see that basically what's the difference? The starting material, the HNO3, and the ending material, the NO3, are very similar. The only difference is that it lost its proton, right? So HNO3 goes from HNO3 to NO3. It lost a proton. The acids give away their protons. Versus the H2O to the H3O, the difference again is a proton. The H2O only had 2 protons, 2 H's, and at the end it has 3. So it's got 3 protons afterwards. And those are related to each other kind of from the product side versus the reactant side, what number of protons you have. So when we do that, so what's this NO3 molecule over here sometimes is called what's the conjugate base. It's basically the HNO3, the acid, without the proton. So if you took an acid molecule and you took away its proton, it would go from HNO3 to NO3 as it goes from the acid to the product side. And that's the same as having the NO3 over here, just without the proton on it. So the conjugate base is what's left over after the acid has given away its proton. So acids and their conjugate base, the only difference between them is one has an H and one doesn't. So for the NO3 sample over here, the HNO3 has an H, it's an acid, and then it gives its acid proton to the water, and it becomes NO3. And the same thing over here with the HCl. The HCl has an H, and it goes and gives its proton to the water, again to make an H3O, and it just becomes Cl. Cl minus is the conjugate base, therefore, of the HCl, just like the NO3 minus is the conjugate base of the acid HNO3. So we see here kind of their acid is the HNO3, the base is the H2O, and then after the H2O gives away its proton, the NO3 is the conjugate base because it doesn't have that H anymore. And the same thing down here with the salt and the HCl. The HCl gives away a proton. It was the acid. It loses a proton. And after it's lost its proton, it becomes Cl minus, which is the same as HCl, just minus an H. So HCl is the acid, and then the Cl is the conjugate base of that acid. And because in both of these cases, the water is the one that took the proton, the water is going to act like a base for both of these samples because the water accepted that proton and went from H2O to H3O. So it has one more proton than it did before. So that's kind of the definitions of what an acid or a base is. And then if you have an acid, you're usually left over with what's called the conjugate acid because all the non-H parts are still going to be in solution because we're still conserving matter, right? We started with 3 H's on this side, a Cl and an O, and then we end with 1 Cl, 1 O, and 3 H's. So all those acid components or the conjugate base of the acid is still there. It's just in another form missing its proton. So we want to have a special term to kind of describe what that is. So for any of these, you can kind of see, right, like what's the acid or what's the conjugate base. And we've actually kind of wrote them all out on the same side, right? So they're all over here. What these all have is these all have H's on them. So these are all the components that contain the H's over here. And then over here, the H is missing. Over here, the H is missing. Over here, the H is missing. So these are all conjugate acid-base pairs. The HCl is the acid. The Cl minus is the conjugate base of that acid because it's missing its H. Or the HNO3, and then the conjugate base of that is the NO3 because it's HNO3 missing an H. Or H2SO4 missing its H becomes HSO4 or SO4 minus 2. So these are the conjugate bases over here because they're just missing their proton from those. So those are some examples of like an acid, but then the conjugate base as well is just the acid minus that proton or minus that H molecule. And the same thing if we take that same atom and we go and remove these as kind of the pairs for the different reactions. So you can see over here a little bit better example because it's a little bit more like the reaction, right? We started with HCl, that's going to be the acid. So we'll do the acids in green, right? So HCl or HNO3 we've established are both acids, but then when it loses that proton, it's going to lose that H from there. So just like over here and over here. So these are all our acids that contain different amounts of H. But then over here, there's a Cl minus, right? No H attached to the Cl anymore. Or over here, a PO4 minus, no H attached to that anymore. Or an SO4 minus, no H attached to that SO4. So basically the acid, when you take away its protons, when you take away its H's, it's going to leave you with the conjugate base, and that's going to be what's left behind. We also had some bases over here, which I'll just kind of underline. So the NaOH, the aluminum carbonate, the MgOH, those were all bases because those all accepted this proton. So they all took the H from there. So right, where'd this H go? This H went and reacted with the NaOH and it made water. Or this H over here reacted with this aluminum molecule and it made a water and a CO2. Or this H over here reacted with this OH molecule over here and made an H2O. So those are all the bases in yellow that reacted with the acid. So acids and bases always react with each other. The H goes away from the acid, it goes to the base, and that leaves you behind the conjugate base, and usually water actually is another product from these reactions. So that's kind of the general definition of what an acid or a base is. And it turns out that water itself can actually act as either an acid or a base. So if you were to look at water molecules on their own and look at what they do, you would see that a very small amount of water, the average concentration of a water, just like a glass of water, if you took some water and you were to count how many water molecules there are, or if you figure out the density of water and use the density of water to figure out how many molecules are present in a water and density, it comes out to be about 56 moles per liter of water. So 1 liter of water contains 56 moles of water molecules. There's lots of water molecules present in a cup of water. So 1 mole of water normally has about 56 moles of H2O. But if you were to look at kind of the H2O molecules themselves, you would see a very, very small amount of the H2O are either in the present of the OH form or the H3O form. And it's a very small amount. 10 to the minus 7 is this number right here. Very, very small amount. So a very, very tiny amount of water is as this H3O. But there is a little bit of it there. And it turns out that if you just let water sit on its own, it'll go to an equilibrium where about 56 moles are in the H2O form, and then 10 to the minus 7, or 0.0000001 moles of water are either in the H3O or the OH minus state. And this is called the auto-ionization of water. Auto means it kind of happens automatically, or it happens by itself without any input. And this just happens. It just very slowly happens. Very, very small amounts of water, therefore, though, are in the acid form of the H3O, and very, very small amounts of water are in the base form of the OH. So very small amounts of acid and base exist just naturally in water on their own. No input from anyone, it just naturally occurs there, but it's a very, very small amount that's normally naturally present in the water. And generally, when the amounts of acid and base are equal, that's what we call a neutral solution. So even though there is a very small amount of acid in water just on its own, it's the typical normal level of water, and we kind of treat that as the base from which we go further. So if there's more acid than normally present than this 10 to the minus 7, then we start to say, okay, now the water is becoming acidic. Or if there's more base than normal, normally there's 10 to the minus 7 base, but if there's a little bit more than that, we say, okay, this water is starting to become basic, there's a little bit too much OHs. But there always is a small amount of H and a small amount of OH in water, no matter what, and you can't really do anything to prevent that. That's just there normally, but they're usually there in about the same amount, and they're very, very small concentrations. So that's kind of this idea that basically water is in these normal conditions, but if there's more acid, so if normally you're at 10 to the minus 7, normally, the amounts of acid and base are equal, and that's kind of your typical neutral solution. So that's what we're going to call a solution that's neutral, no difference in the amount of acid or base. But if for some reason you add a little bit more acid to that sample, and you go from 10 to the minus 7 acids and 10 to the minus 7 bases to maybe 10 to the minus 5 acids, now you got a lot more acid than you do base, and that solution becomes acidic. So any solution where the concentration of H3O is higher than the concentration of OH, we're going to call an acidic solution. And any solution that's opposite, where the OH concentration is higher than the acid solution, we're going to call that basic, or in a solution where the H3O concentration is less than the acid solution. So if there's less or more, then whatever one you have more of, so, right, if you have more H3O, you're an acid. If you have more OH, then you're a base. So if you have more of a base, then you're basic. If you have more of an acid, then you're acidic. And that's typical for water. Water normally is neutral because the amount of acid and base is equal. But if you go and add more acid to the water, you can make it acidic, or if you add more base to a water, you can make it basic. And actually, it turns out what's kind of neat is that the temperature of water actually changes slightly whether or not water is acidic or basic. So you can kind of draw a little line to kind of see these. So at room temperature, which is where we are, so we're down here, the room temperature of water, the pH is 7, and that's what we'd call neutral water is pH 7. But if you heat up water, it actually becomes more acidic, or if you cool down water, it becomes slightly basic, even though it's still, by default, the concentrations are the same. So the temperature of water can actually change the pH a little bit. And this is where when people talk about global warming and they worry about the oceans becoming more acidic, that's because as you increase the temperature, you see you go from a pH of about 7, even a couple of degrees, you go slightly lower than that. So the pH of the oceans can change, and that can cause a lot of problems to the animals that live in the ocean. The way, if you're a shell animal, if you're an animal that has a shell like a clam or a snail or some kind of other animal with a big hard shell, as you lower the pH, those shells actually become more soluble and your shell can start to dissolve. And that wouldn't be very good if you're an animal that lives in a shell. You wouldn't want that to happen. So the pH of oceans and waters is important, and the temperature is important for controlling that. So that's one of the things that when people talk about global warming, they talk about the acidification of the ocean. That's what they're referring to. As the temperature increases, the pH actually will become more on the acid side. So this is the acid side down here, and this is the base side over here. And it's not a lot, but it is enough to make a little difference. Even a few degrees will actually change that pH. So that's what you may have heard about also. But acids and bases are linked. So the concentration of the acid and the concentration of the base component of the water, you can figure out one, as long as you know one of them. So if you know what the concentration of water is, and you know what the concentration of the acid in the water, what the H3O concentration in the water is, then you can figure out what the concentration of the base is as well. They're linked together. And if you ever needed to calculate that, there's a little equation here. You don't need to know anything specific about it, but if you ever needed it, we can always give it to you. But if you're ever curious, if you were wondering how much OH is in water, but they only tell you how much H3O there is, or maybe they tell you how much OH is present in water, and you want to know how much H3O there is, then you can figure that out. So if you know the OH concentration, the H3O concentration is just 10 to the minus 14 divided by whatever that concentration of OH is. And likewise, the concentration of OH is whatever is 10 to the minus 14th divided by whatever the H3O concentration is. So if you were ever given one, but you wanted to know what the other one is, there is a little equation that you can use here to actually figure out one to the other and convert those. So that's just a useful thing if you ever were reported one number and you want to know what the other one was. And then because we know that acids are when the H3O is higher and bases are when the OH is higher, then you can compare what's the H concentration, what's the OH concentration. Is one higher than the other, or are they the same? If they're the same, we're basic and neutral. If the OH is higher, we're basic. If the OH is lower, we're acidic. And we could actually figure that out as long as we know one of the two. So this is just an example of doing one of those calculations, right? So they tell you you have a sample, it's 10 to the minus 4 molars of H3O solution, and you're wondering, oh, that's a pretty number, it's 10 to the minus 4, it's bigger than 10 to the minus 7. Is that acid or is that a base? And you could actually figure that out. So you could use this little equation, right? We know that OH is equal to 10 to the minus 14th divided by the concentration of H3O. We have the H3O concentration here is 10 to the minus 4, so we're going to just put that down here. So we can do that. So 10 to the minus 14 divided by 10 to the minus 4, which is the H3O concentration, that comes out to about 10 to the minus 10th. So the OH concentration is 10 to the minus 10. The H3O concentration is 10 to the minus 14. And 10 to the minus 10 is a smaller number than 10 to the minus 14. So the H3O concentration is much larger than the OH concentration, because 10 to the minus 4 is a bigger number than 10 to the minus 10. 0.0001 is much bigger than 0.00000000001, much larger number. So that means that this is what's called an acidic solution, more H3O present than OH in that particular solution. So the H3O concentration is high, the OH concentration is low. That makes this solution an acid. So we could figure that out if we ever wanted to do that, given some numbers here, if we were ever asked about that. So this is another example of the same type of equation calculation like we did before. This time we have a slightly different concentration of H3O, 10 to the minus 8 moles per liter H3O in a solution of water. And again, they're asking, is this an acid or is it a base? And since we have the amount of H, we can also figure the amount of OH, and we know that OH and H are linked. 10 to the minus 14 divided by whatever the H is, and in this case it's 10 to the minus 8. So we can plug that in to that part of the equation right there. So we divide 10 to the negative 14th by 10 to the minus 8, and that'll give us the concentration of OH that is in solution. So this solution has 10 to the negative 6 moles per liter of OH, and it has 10 to the negative 8th moles per liter of H. So we can compare how much H there is versus how much OH there is and figure out, is there more H? If there's more H, then it's an acid. Is there more OH? If it's more OH, then it's a base. Or are the H and the OH values the same, in which case it would be neutral? So we can compare those two numbers. OH is 10 to the minus 6 as we calculated. H is 10 to the minus 8th. So 10 to the minus 6 is a little bit bigger number than 10 to the minus 8, which means that there's more OH in this solution than H, which means that this is a base. So we can do this for any solution if we have the OH concentration or the H concentration. As long as we have one, we can calculate the other, and we can figure out whether it's an acid or a base. So this is that same type of calculation, except now they want us to calculate the amount of H3O instead of the amount of OH, because they gave us OH. So we have 10 to the minus 7 moles per liter of OH, and they're asking again, is this an acid or a base, or is it neutral? We know how much OH there is, and we can convert OH into H using the same equation, 10 to the negative 14th divided by whatever the amount of OH there is. In this case, there's 10 to the negative 7. So we plug that in, 10 to the minus 14 H3 divided by the amount of OH, 10 to the minus 7, and that in this case comes out to be 10 to the negative 7 moles. So we've calculated that there's 10 to the negative 7 moles of H. There's also 10 to the negative 7 moles of OH from the instructions at the beginning. So in this case, the amount of H and the amount of OH are equal. So since those two amounts are equal to each other, that means that this is a solution that's neutral. It's not an acid or a base, it's neutral. The amount of acid and base are both the same, so the amount of acid and base cancel each other out. They're both 10 to the negative 7. So that's some calculations, and rather than doing all those calculations frequently, you can kind of use tables. So this is a table that we made to kind of show how do concentrations of H's and OH's compare, and is that solution an acid or a base? So like we'd said earlier, if your concentration of acid H3O and your solution of base OH is the same, then you have a neutral solution. So that means you have usually about 10 to the minus 7 for both of those. But if the acid concentration, like we said before, right, 10 to the minus 10 and 10 to the minus 4, that's the example we just did, you can see that's an acid solution, versus if you had 10 to the minus 13th for an acid concentration, you'd probably have closer to a 10 to the minus 1. If you did that calculation we just did for all these different OH concentrations, you could figure out the H3O, or you could do it the other way around. But if you don't like specific notation, you can do this with decimal notation too. And now you can kind of see how basically as the acid concentration goes up, the OH concentration gets down. So when there's a really high acid concentration, the base concentration is generally very, very small. And then opposite happens as the base concentration increases, the acid concentration goes down. So this is kind of showing that trend of this becoming larger as this becomes smaller. So that's kind of the idea of acids and bases are linked. The amount of H3O in a solution and the amount of OH in a solution are tied together by that 10 to the minus 14th number. So really, really high concentrations of base means that you have a really low concentration of acid, or if you have a really low concentration of acid, then you have a really high concentration of base. and backwards. So that's kind of some calculations we can do, and you can kind of see this all over the place. But when we're talking about concentrations, we're not talking about very high in the end. 1 molar acid compared to 56 molar water, right? Water has a solubility concentration 56 moles per liter. A really strong acid might only have a concentration of 1 mole per liter. And then a weaker acid, maybe a lower concentration of acid or a near neutral solution, 10 to the minus 6, 10 to the minus 7 moles per liter of acid. So you don't have to have a lot of acid present to start to cause some effects on these samples. Even a pH of 5 or these kind of medium concentrations up here are already going to start to cause some acid effects. So you don't need a lot of acid or base in solution to start to see some effects happening. And you can actually see it at relatively low concentrations. The concentrations we're usually working with are in these ranges here, and that's enough to cause a reaction to happen, even though the concentrations aren't very high. But when we're using all these numbers, rather than saying, 10 to the minus 14 and 10 to the minus 13, 10 to the minus 10, 10 to the minus 4, or writing them out, 0.000001, that's a lot of writing to do. And people like to do things like scientific notation or other methods, but also negative exponents. They're kind of hard to see, right? 10 to the minus 14, you can easily lose that minus sign, and then you might not be able to read the number right. So what we do is, rather than expressing and saying that this coffee right here or this drink that I'm drinking has a concentration of 10 to the minus 3 acid molecules per liter, then rather than doing that, what we'll do is we'll report it in a unit of what's called the pH. And pH, whenever you see a P, that usually means the negative log of the thing after it. So the pH is the negative log of the H, or in this case, the H3O. So you could say it's the pH3O. They wanted to make it a little bit simpler sounding. It's the pH. And you've probably heard about pH before on various things. pH tells you basically how much acid is present in a solution. But rather than saying that this acid solution has a 10 to the minus 5th concentration, they'll just say it has a pH of 5. So whatever the concentration of the H3O is, take the negative log of that number, and it'll give you the pH. So if you had a sample that was 3 times 10 to the minus 2 H plus concentration, it's going to be a pH of about 2. And you could put the negative log of 3 times 10 to the minus 2 and you'd get a number, but you'd get a number pretty close to 2. So if you don't know what the pH of a sample is, it's just the negative log of the H3O concentration. So if we had a sample here, like this one, 10 to the minus 8 H3O, well, the negative log of 10 to the minus 8 is 8. So we'd say that this sample has a pH of 8. And you can do the reaction backwards too. So if they told you something has a pH of 5, so your sample has a pH of 5, then that's saying that it has a 10 to the minus 5 concentration. Or if you had a pH of 7, 10 to the minus 7. So you can go forward or backwards with pHs, depending on whether they give you the acid concentration or if they give you the pH. So this is just kind of saying also, though, if you think about what the numbers are, right, when your sample's neutral, when the pH is from 10 to the minus 7, that means that your sample's neutral when it has a pH of 7. Or we figured out that acids generally have an H plus concentration that ranges from 10 to the 0 to 10 to the minus 7. That means that acids are samples that have a pH of less than 7. And bases are when the OH concentration is more higher than the H, which means the OH concentration is 10 to the minus 7 through 10 to the minus 14. That means that bases are samples where the pH is greater than 7. So whenever we're looking at acids and bases, we can give you the H concentration or the H3O concentration. We could give you the OH concentration, but we could also just say this is the pH. And if you kind of remember that acids are pH from 0 to 7, bases are pH 7 and above, and neutral is when the pH is equal to 7, then if you hear that you're drinking some coffee that has a pH of 5, then you know that coffee is a little bit acidic. And the farther you are away from 7, the more acidic it is, or the more basic it is. So if I was drinking some water with a pH of 8 and some water with a pH of 11, then you know that 11 is more basic, the 8 is closer to neutral. And just to kind of put some stuff into scale here, here's some different materials. I gave you the H3O concentration in moles per liter. we give you the OH concentration in moles per liter. We also just took the negative log of the H3O. So the negative log, for instance, of -2 is 2. So you can see the pH. So you can see that samples with pHs from 0 to 7, those are acidic. Samples with pH of 8 or higher are basic. And then a sample with a pH of 7 is neutral. And then we gave some examples too. So think about different materials that you might have come across. So pure water and even things like your blood are generally about pH 7. They're pretty close to neutral. But a lot of different kinds of juices and stuff around your house that you eat is frequently acidic. A lot of naturally occurring things that we drink in terms of juices and nutrient materials are neutral, or acidic. So water is neutral, but milk is slightly acidic. Milk has a pH of 6, so just a little bit less acidic than pure water, is a little bit off. And then things like coffee are a pH of 5, that's a little bit more acidic. And then a lot of the different juices you might drink, like orange juice or lemon juice or vinegar or some sodas, those all have pHs in the 2 to 4 range. So those are all pretty acidic, much more acidic than your coffee or your milk or your pure water is. And then that's about it for naturally occurring acids in terms of foods that you may eat. But the stomach, your stomach also has an acidic environment to help you break down and digest food. And your stomach has an even lower pH of 1. So your stomach acid is more acidic than the lemon juice you may have around your house, or the orange juice you might have around your house, or the vinegar you might have around your house. So it's pretty acidic. And since your stomach is essentially hydrochloric acid, it's a little bit less acidic than pure hydrochloric acid that you might find in a lab, but it's up there in terms of corrosivity. And if you ever have like acid reflux or anything where you've been exposed to your stomach acid, then you know that it is pretty corrosive. You can feel it kind of burning because it does. It dissolves proteins. It dissolves molecules. Stomach acid's pretty corrosive because it is a pretty concentrated acid with a pretty low pH. Low pH, the farther you are from 7, the more acidic your content material is. The higher the H3O concentration is, the more acid content you have. So pH 1 stomach acid is pretty acidic. We can go the other way too and see things that are more basic. So just like water in the ocean with the salt in it has a pH of about 8. Baking soda has a pH of around 9. Ammonia, you might clean your house with pH 10. And then as you get farther away from 7, you get toward 8, 9, 10, 11, you become more basic and much more higher concentration of base. You can see the base concentration increasing as we go farther away from pH 7. So the higher the pH, the more concentrated the base is. And then you get to things like bleach or drain cleaner for some extremely basic samples. So you'll see a lot of the cleaning material supplies we use are very basic. A lot of the acids and juices that we get exposed to are more on the acid side. But these are just some naturally occurring bases or acids you might see around your house. Again, showing that the bases have a pH of 7 or higher. The more concentrated the OH concentration, the lower the H gets. So as H goes down, OH goes up. And as OH goes up and H goes down, the pH also increases as well. You get farther away from neutral into the more basic side of reactions. So just to do one quick example, right, we have a sample 10 to the minus 4 H3O. We want to know, is that an acid or is it base? Well, we know that pH is equal to 10 to the minus negative log of H. So negative log of 10 to the minus 4. And then we put in that number here. We can calculate out what is the pH. So negative log 10 to the minus 4 comes out to 4. And samples that are pH less than 7 are acid. So this pH is much less than 7, it's 4. So this is an example of an acid. So this is how you could use pH to kind of figure that out. So if you're reading about different materials and you're wondering, am I working with an acid or a base? You could either look and see what pH it has recorded, or if they didn't give you the pH, but they give you the concentration of either H3O or OH, we could figure it out and convert it that way. This is just another example here, right? So now we have another sample, 10 to the minus 8 moles per liter. Again, the negative log of 10 to the minus 8, because that's just the H. And that tells us this sample has a pH of 8, which is higher than 7, which means it's a base. So just another example of how we could actually figure out if we either knew the H concentration or the OH concentration, we could figure out the pH of a sample. So we can use the pH scale that we talked about also to figure out if something's an acid or a base, as long as we have one of the two samples that we need to know, either the amount of OH or the amount of H3O. Here we've gotten a sample where they told us the amount of OH that's in solution, and they want to know the pH as well as is it an acid or a base. So we have the amount of OH that's there, but we want the pH. pH needs the amount of H3O. We don't have H3O, we have OH. But we can always turn OH into H3O using our conversions. We know that the amount of H3O is equal to the Kw, or 10 to the minus 14th, divided by our OH concentration, in this case 10 to the minus 7. So we can put those in, 10 to the negative 14th divided by the number of OHs, or 10 to the minus 14th divided by 10 to the negative 7. And that gives us an H3O concentration of 10 to the minus 7 moles per liter. So now we have our amount of H3O, and we can put that amount of H3O right here into the equation to tell us the amount of H3O, take the negative log of that number, and that'll give us the pH of this sample. So the negative log of 10 to the minus 7 turns out to be 7, which means that our sample has a pH of 7, and that means that it's a neutral sample, because when you have a pH of 7, you're neutral. When you have a pH of 1 to 6 and to less than 7, that's an acid. If you have a pH that's more than 7, that's a base. In this case, we're at exactly 7, so we have a sample that's neutral pH. And this is just two more example calculations in more of a multiple choice type version. So here we go. We have a version multiple choice, a couple different pHs to choose from. And it says that our sample has an OH concentration of 10 to the minus 4. They want to know what the pH is. So we know that pH is equal to the negative log of the H concentration, the H3O, not the negative log of the OH like they've given us. So we're going to have to turn OH into H first. But that's okay, we can do that just like we did before, 10 to the negative 14th divided by the OH concentration. So we have 10 to the minus 14 divided by 1 times 10 to the minus 4. And when we put that into our calculator, we divide 10 to the negative 14th by 10 to the minus 4, and we get 10 to the minus 10, which means that our H3O concentration is 10 to the negative 10, and that's what we're going to put into the negative log. So the negative log of the H3O, or the negative log of 10 to the minus 10 moles per liter, will give us the pH. In this case, the pH is 10. So we would go through and pick the sample that has the pH of 10. So that would be the way of solving this type of problem here and seeing what is the pH of the solution. They gave us the amount of OH, we turn that into H, and then we take the negative log of the H to get the pH. Slightly different version of a question would be asking how would you classify a solution that has 10 to the minus 4th times 5 moles of OH. And this is a little bit different number than the one we've been seeing, but again, we can just plug this right into the concentration. So 5 times 10 to the negative 14th, we would put that in down here. 10 to the minus 14th divided by 5 times 10 to the negative 4th moles per liter of OH. And that tells us that the amount of concentration available in this particular sample of H3O is 2.5 times 10 to the negative 11 moles of H3O. And then we would compare how many moles of H3O are there. There's 2.5 times 10 to the negative moles of H3O versus the amount of OH is 5 times 10 to the minus 4th. This is a much bigger number than this number here. So that means that there's much more OH than H present in the solution. And when there's more OH than H, that means that you have a sample that's a base. So this is a basic sample because there's more OHs than H's present in the solution in that case after we do this calculation. Or if you have a fancy meter, you can also measure it. So maybe you don't know the H3O concentration, maybe you don't know the OH concentration, but you want to know is something an acid or a base. There's a couple of different ways to figure it out other than looking up the H and the OH concentration. You can either use an electronic meter, like a pH meter over here, which is a digital device, kind of like an electric thermometer can measure temperature using electronics. A pH meter can use electronics to actually measure how much H pluses are present in solution. Those have a H plus is a charged unit. It's an H plus, it's a positive ion. And that actually causes the sample to have a very, very small amount of electrical conductivity. And it conducts electricity through the sample. So by using a very, very sensitive electronic device, you can actually measure how many H's are present in solution. And since pH is related to how many H's there are, you can measure the pH. So that's one more modern kind of method. So if you're concerned about maybe the rivers behind your house, or down the street from you, or one of the rivers near a road, and you want to know, well, there's a lot of acid coming off of the road maybe. Is that acid getting into the water in the stream or the lake around here, and that maybe is causing the lake to be more acidic? You could get an electronic pH meter and you could go and measure the pH and see, is this lake more basic? Is this lake more acidic? By looking at the pH. Is the pH either more or less than 7 versus about neutral? And that's one way to do it. But not everyone has a pH meter, and pH meters are relatively new. So before they had pH meters, or if you just don't have one, the other way you can do this is by using what are called indicators. Indicators are pretty cool. They're compounds, they're chemical dyes that actually change color depending on what their pH is. So they have a chemical that's sensitive to acid or base, and as the sample becomes more acidic or more basic, they actually will change colors. So one of the examples is this top compound here, that depending on what pH it is, if you're at a pH of 2 or a pH of 4, it's a nice pink-red color. But if you're at a pH of 6, it turns orange. And if you're at a pH of 7 or 8 or 9 or 10 or 11, it turns yellow. So if you want to know, is my lake acid or basic, and you were worried that the lake may be acidic, you would take some lake water, you would add this indicator to it, and if the solution turns orange, then you could say, okay, it's pH 6, that's acidic, but a little bit. Or if the pH turns reddish, you can say, okay, the pH is somewhere between 5 or less. So you can kind of do that. But then you want to know, you could use multiple different kind of chemicals. Other chemicals go from like yellow to blue. So this sample here, the cutoff is around 7. So if you're below 7, you're yellow. If you're above 7, you're green. So you could actually kind of do some combinations and figure out, well, maybe your lake sample turned yellow. So you know the pH is higher than 7. Your lake sample also turned blue, so you know it's higher than 7. But for this last compound here, your lake sample didn't turn red, so you know it's not 10 or 11 or 12. You know it's kind of in this spot here. So by using a couple different indicators, you can actually figure out what the exact pH is. And you can get these little strips actually that are basically a bunch of indicators on them together. So one, it's 3 little boxes, and one indicator is the top, one indicator is the middle, one indicator is the one on the bottom here. And then you kind of compare the chart and figure out where does your strip fit on the chart. And that tells you actually what the pH is. So you can get these little test kit strips if you want to go around and test the pH of different liquids in your house or different bodies of water around your house. See how acidic the lake is. See how acidic the river or the stream was. You can check it with these little test strips, and they're relatively cheap, a lot cheaper than buying a pH meter. So you can do that if you're interested in the environment and the pH of various things around you. So that kind of leads this idea of, maybe you want to know, is the water around your house contain acid? Because acid rain is a pretty big deal, especially around the part of the country where we live. So rainwater, normally like regular water, should be a pH of about 7, neutral pH. But acidic compounds can get dissolved in the water. And those compounds are usually dissolved in the water, and they form both sulfuric acid and nitric acid. Those are both 2 types of acids that can dissolve in the water. And when those go into water, they cause the water to become acidic. So the water can either rain down from the sky as rain, but it can also be snow or fog or hail. So not only can you have acid rain, you can have acid snow, you can have acid hail, you could have acid fog, which would be very bad because it's very kind of sticking in the air and it can kind of hit everything. And these are problems, especially for regions with high pollution. So where does the sulfuric and nitric acid come from? Well, it comes from when we burn fossil fuels mostly. So about 66% or 2/3 of the sulfuric acid that we get in the air is from power plants, especially coal burning power plants. About 25% of the nitric acid that's in the air is from power plants as well. Also, though, it does come naturally too. So if you live near a volcano, huge volcanic eruption, that's also going to cause there to be some nitrates in the air and sulfates in the air. And the areas around that concentration of that volcano can have acid rain as well. But most of the acid in the air that we get is from pollution. And this is just kind of a little chart from the EPA showing that if you have a big factory, it puts out all these SO2 and NO2 molecules. And those get up into the air. And it's not just the area around the factory, because the clouds can go really, really far distances. And then it can either rain out as acid rain, it can fall out of the sky as acid snow. But then that rain and that snow eventually gets, accumulated, gets into rivers, and then those rivers can make their way to larger streams and oceans too. So it doesn't necessarily just have to be the local environment around these factories or these power plants that cause this. It can have some pretty widespread effects. If you look at the US, you can see that certain parts of the country have more acidic pH or acid rain versus areas that are more less acid rain. So there's kind of a line here where the acid rain gets really particularly bad. And this was just by going around NOAA, the National Atmospheric Testing Agency, and a few other agencies went around and basically checked what is the pH, how acidic is the water in various parts of the United States. They looked at both rainwater and rivers. So this is mostly from rainwater in this particular graph here. And if you look at the US, where all the power plants are, you see that same kind of divide. So we see that same kind of divide here, where the region becomes much more acidic rain versus over here. So regions of California, not too much acid rain, but there's also not too many power plants over there. Versus over here, very high concentration of coal burning power plants and pretty high concentration, and it actually moves its way up a little bit because it doesn't just stay in the local area, it spreads around, and it can go either north or south or east, depending on which way the wind blows. Generally, winds blow kind of these directions. Oops. This way, and this way. So you can see how the area just slightly north of all those power plants has a very high amount of acid rain from all the different combustion of all those fossil fuels. So burning fossil fuels puts those molecules into the air. Those molecules react with water and they create an acid environment. And then that acid can fall out of the rain as a solution of SO4, HSO4, HNO3, which are all acids. So those are all acids, and those are what acids are. And the reason why acid rain can be concerning is because acids undergo certain chemical reactions. Acids will react with bases, acids will react with metals, carbonates. So if you're a carbonate, carbonates are things like shells. So if you're a shell, then carbonate's really bad. Also, if you're lime or limestone, this is bad. So if you have a building made of limestone and you live in an area with high acid rain, you'll actually see the building is pitted. It looks like somebody like dug away at it almost, or like, how like mud kind of washes away and gets wrecked. Same idea. It looks like the building actually started to dissolve. So acids can react with lots of different materials, and they undergo various kind of reactives materials, and they'll also react with metals. So acids can also react with metals. So even if you have a steel building, then your acid rain could actually start putting little pits and holes into the steel. Or if you have a car, it can get wrecked. So anything made of metal or anything made of rock or stone, lots of things are sensitive to acid. Acid can cause a lot of different types of reactions, and it dissolves these materials. And this is just showing how different metals will react to acids differently. So some metals are a little bit safer or a little bit more protected from acid reactions than other metals, what materials will. So certain metals like potassium, sodium, calcium, those are very, very reactive. So sodium will react with anything that's an acid, including water. Water is a very, 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 very low concentration of H+. It's essentially neutral, but there is a small amount of H3O. So some things like sodium and calcium, even the tiniest bit of H3O, even the H3O present in neutral water is enough for those molecules to react. Other things like aluminum will react with acid as well. Usually for a little bit stronger concentration acid, so something like pH of 5. And then things like iron and nickel and lead, they're a little bit more safe from reactions. They need a very high concentration of H3O. So the pH of 5 isn't enough to react with lead or iron, but a pH of 3 is. So if I took some lead and I put it in pH 1, it would react. In pH 2, it would react. pH 3, it would start to react. But at pH 4 or 5 or 6, it wouldn't react. So that's okay. But that's why, again, when we talked about lead and lead pipes and materials like that, they were worried about at very low concentration, lead starts to react and dissolve. So if the water becomes too acidic, then the lead leaches out of the pipes and goes into solution, and it can cause a problem. And then the most safe react metals to have around acids are things like copper, silver, platinum, gold. These are all those metals that we use to make expensive coins and fancy jewelry. And you can see that you can basically take copper and you can put it in anything except a pH of 1. So if you put it in pH 2 or 3, nothing's going to happen. But if you put it in pH 1, it's going to start to dissolve and become pitted as well, just like gold and silver and platinum. So these metals are relatively low effects. But this is why if you buy like a fancy aluminum water bottle, there's a warning usually on the side of it somewhere when you get it on the sticker. Something that says, do not put soda or juice into this bottle, only use it for water. And the reason for that is because aluminum reacts with anything with a pH of 5 or less. And so milk has a pH of about 6, that's fine. Coffee has a pH of about 5, that's maybe okay. But if you look at the back a few slides, when we talked about the different materials like juices, sodas, lemon juice, orange juice, they also have pHs of 2, 3, 4. 4 is a pH that's lower than 5. 2 and 3 are lower than 5. So if you took some orange juice with a pH of 3 and you put it in your fancy aluminum water bottle, the acid in the orange juice is going to start to react with the aluminum, and it'll actually start to dissolve the aluminum and put little pits in it. So if you ever have a water bottle that you filled up, an aluminum water bottle that you filled up with soda or juice, you may notice it's got this little kind of rough, it almost feels like sandpaper inside. That's because the acid in that juice or that soda reacted with your aluminum water bottle and actually started to dissolve it. This doesn't happen with soda cans because there's actually a layer of plastic inside. So the reason we can put aluminum into a soda can and not have the soda dissolve its way through the can is because it actually has a layer of plastic between the can and the metal, so that doesn't happen. But if you don't have that layer in your water bottle, then it'll start to dissolve. And this is just showing what happens if you took 4 different metals, one kind of from each series. So the one that reacts with pH 7, one that reacts with 5, one with 3, and one with 1. And what I did is I put them each into a jar of acid that has a pH of 3. So this is a pH 3 sample. And you can see the copper, really nothing's happening, right? Because copper will only react if the pH is 1 or lower. And 3 isn't lower than 1, so it doesn't react. Meanwhile, the iron is very slowly reacting because this is a pH of 3, and iron will react with something with a pH of 3. But the other two guys, the copper and the calcium and the zinc, those will react with anything with a pH of less than either 7 or 5, and 3 is lower than both of those numbers. And the calcium reacts kind of really, really violently, and you can see a lot of bubbles coming up, versus the zinc's a little bit more slow. But you can see how, therefore, different metals are kind of sensitive to different amounts of acid present. And if you have more acid, it'll react a little bit faster. If you have less acid, it's a little bit slower. But some metals are more sensitive, that things like calcium, even pH 7 calcium will start to react, because even the pH present in neutral water is enough for that calcium to start to do its reaction there. So if we had a problem on a test that might ask kind of what's the best metal for storing a particular material, you would want to look at the activity series and figure out what metal works the best compared to the acid that you're working with. So in this particular example here, they're talking about an acid that has a pH of 3. So we're working with an acid that's a 3 pH, and we're looking for a metal that won't react with acids that are pH of 3. So if we have an acid that reacts at pH 7, 5, or 3, those would all be not very good. We'd want something that only reacts at pH 1 or lower. So we want something that's very high on the acid scale, so very, very low pH or stabler. So if we look at these choices, right, so we have potassium is going to react with an acid of pH of 7 or lower. Well, 3 is lower than 7, so 7 versus 3, that's no good for the potassium. Same thing for the aluminum. The aluminum is going to react with 5 or lower. 3 is lower than 5, so it'll react with the aluminum as well. So if you put HCl into an aluminum bottle, it'll react and it'll start dissolving the bottle. That wouldn't work. The next choice was lead. Reacts with acids of pH 3 or lower. Well, pH 3 is 3, so that's not the best choice, but it's the best one we've seen so far. So that would be an okay choice, but there is a better choice, and that would be, in this case, the platinum, which only reacts with pH 1 or lower. So that's our best choice available, to have this platinum sample here. Because our sample has a pH of 3, it's going to react with stuff with a pH of 7, it's going to react with stuff with a pH of 5, it's going to react with stuff with a pH of 3, but it won't react with pH of 1 because 1 is lower than 3, so pH 3 is higher than 1, which means that that particular material doesn't react. So if you're looking at these type of reactivity series, you want to be the sample that's not going to react, and in this case, that's a sample with a pH of 1 or more is needed to react with this, but this acid only has an acid pH of 3, so it won't react. But if the acid had a pH of 0, it would react with the platinum as well and wouldn't be any good. So in this particular case, that's the sample we're going to use. So that's acids with metals, but acids also react with bases too. So acids react with lots of different stuff, metals, bases, lots of different materials. When acids react with bases, what's actually kind of neat is that basically the acid gives away its proton, the base takes the proton from the other one. So they basically trade a proton, and frequently they make things like salt and water. So if you take an acid like HCl and a base like NaOH, what's going to happen is this H goes away from the acid and over to the NaOH, and then they produce salt and water as kind of two side products there. So that's kind of the idea of an acid and a base will react together for those. And when you make a salt is basically any metal non-metal pair. The metal is the ion that came from the base, and the anion is the part from the acid, the non-metal, and they come together. So just like a cat has paws, cations are positive, cations are the metal ions that came from the base. So just to kind of show you some examples, right? If you took that HCl, which has the cation, the Na, the metal ion from a base, and then the Cl, the anion from the nonmetal, that's going to produce a salt in the end. This NaCl molecule is a salt, and it has both part of the base over here in red and part of the acid over here in green. So both of those are present when you make that final product. And it doesn't have to be NaCl. There's plenty of other salts that exist. So this is just another example of a different acid, H2SO4 reacting with NaOH, which is another base. And this also produces a salt. It produces the salt Na2SO4. And again, the SO4 came from the acid over here, and the Na came from the base over here. So you can make all sorts of different salts. Again, salts are just ionic compounds, metal, non-metal pairs, where the non-H part of the acid and the non-OH part of the base react and come together, just like the H and the OH are reacting with each other in this kind of double replacement, right? So Na was paired with the OH, now Na is paired with SO4. This is a double replacement type of reaction like we talked about earlier. So one final example of an acid-base reaction in a salt would be this example here, which is looking at HCl, again, which is an acid. So HCl is an acid, and the HCl contains a Cl-, which is the anion from the acid. This is the non-metal component of the acid. Cl is over on this side of the periodic table, versus the aluminum is on the metal side of the periodic table. So aluminum is a metal, so that would be on the metal side. The chlorine is on the non-metal side. So the metal, the chlorine right here, which is part of the base, is reacting with the Cl, which is part of the acid, and those create a salt, aluminum chloride, AlCl2 in this case. So we have an aluminum metal and a chlorine nonmetal reacting together, the aluminum coming from the base and the metal HCl coming from the acid. Those come together in addition to creating H2O, and in this case also CO2 gas. But we also produce this new salt, this metal nonmetal pair, an ionic compound with a metal, the aluminum, and the nonmetal, the chlorine, together for that sample there. So acids and bases react with each other. If you add an acid to a solution of base, those two chemicals are going to react and produce water. They're going to produce a salt, and that's what's called the neutralization reaction. And we can use that reaction actually if we want to figure out how much acid or base is present in a sample as well. We can take advantage of that. So we could use a pH meter to figure out how much acid or base is present in a solution, but there's other methods of doing that as well. And one of this method is called the titration. So if you had a sample that had acid in it, so say a sample of juice or a sample of coffee or some other vinegar, and you wanted to know how much acid is actually present in that vinegar, what you could do is you could take that sample of vinegar or acid or coffee or juice, and you could take that knowing that there's acid in it, and you could add a base to that acid. So if you took vinegar and you added some base to it, a chemical reaction would occur between the acid and the base. And if you had a way of measuring how much base you add, so if you had a very carefully calibrated burette or some other piece of glassware, you could add base to your acid very carefully, and you could record the exact amount of base that's been added to that acid, and then you could figure out how much base you had. And if you knew the concentration of that base, you could figure out how many moles of base you added to your acid until the sample became neutral and there was no more acid or no more base. And at that point, the number of moles that you added of that base would be equal to the number of moles of acid that were present in the original sample. And this technique is called the titration, and it's used to figure out the amount of acid that's present in a sample by adding an exact, precise amount of a base of a known concentration, and you keep adding that base until the sample becomes neutral. And you can measure neutrality either using a pH meter, or you could use certain chemicals that change color in the presence of acid or base, or change color when they're neutral. And you can do this process either for an acid of an unknown strength by adding base, or you can do this process for a base of an unknown strength by adding acid. So you can do this either way to figure out how much acid or base is present in your solution. And this is just an example of one of those types of calculations. So what we have here is a solution of HCl, and we have half a liter of HCl, but we don't know what the concentration of that HCl is. It's some number of moles per liter, but we don't know what the precise concentration is. But we do have some sodium hydroxide, which is a base. So we have a base and an acid together now. So we have an acid over here, and we have a base over here. And if we add that base to the acid, a neutralization reaction will occur. And we have this base has a 0.1 mole per liter concentration. And we add that base very carefully to our acid until all of the acid and all of the base react with each other. And then we're over here where what we have is a salt and H2O water. There's no more acid present, there's no more base present. This sample would have a pH of 7. So we have a sample with a pH of 7 now, no more acid, no more base, and we know to get to that point, we had to add 0.75 liters of a 0.1 mole per liter solution of base, NaOH, to our half liter of acid. So we can figure out how many moles of NaOH that was. We know that this was a strong acid and a strong base reacting, and the moles of NaOH is just the concentration of the base, the 0.1 moles per liter, times the volume of the base, the 0.75 liters of base. Multiply those by each other, 0.75 times 0.1, turns out we added 0.075 moles of NaOH. And we can see from our balanced reaction here that 1 mole of HCl is going to react with 1 mole of NaOH. So if we added 0.75 moles of NaOH, that means we added 0.75 moles of HCl to our sample, because the moles of acid and the moles of base would equal each other, since this is a 1-to-1 chemical reaction. If we then figure out what the concentration of the HCl is, we know it was 0.075 moles of HCl divided by 0.5 liters, because all those 0.075 moles were contained in half a liter of HCl. So we divide the concentration of HCl, the 0.075, by 0.5 liters of HCl, and it turns out that our acid had a concentration of 0.15 moles per liter. That's the concentration of the HCl of this sample here. So that's a pretty good spot to stop. We'll go over this again next time, but hope you guys have a good day, and we'll talk to you next time. Have a good night. Bye.